Okay. So good afternoon, everyone. It's very nice to have you here today. This is our first American Rock Mechanics Association student chapter at Virginia Tech's guest lecture. So the American Rock Mechanics Association is the professional and international engineering and scientific society that promotes interaction among rock mechanics and geomechanics specialists, practitioners, and academics. In keeping with ARMA's principle that a strong student membership ensures future continuity, the ARMA student chapter at Virginia Tech was created 2 or 3 years ago to expose Virginia Tech students to state-of-art rock engineering and to promote the development of knowledge within the field through research, dissemination, presentations, meetings, publications, and topical symposia. Today, for our first guest lecture this year, we have invited Dr. Brent Slaker. Dr. Slaker has been a mining engineer for the past 5 years in the ground control branch at the Pittsburgh Mining Research Division of the National Institute for Occupational Safety and Health. He currently leads a project exploring pillar design for challenging conditions in underground stone mines. Dr. Slaker has a bachelor, master's, and PhD degree in mining engineering from the mining department at Virginia Tech, where he studied seismic tomography, photogrammetry, LiDAR scanning under Dr. Westman. So today I would like to start with a few words from Dr. Westman, who is our academic advisor, and then we could continue with Dr. Slaker. Hi, Dr. Westman.
Thank you, Juan. Yeah, it is a privilege to be part of this kind of historic presentation, the first one for the ARMA student chapter this year. And I think it's very fitting that Juan is hosting this. And he referred to it as the American Rock Mechanics Association, which is the title. However, I had the privilege of serving on the board of directors of ARMA for 6 years, and clearly the intent of ARMA is not to be limited to North America or even the United States. It is to be an international organization. And so having someone from the great nation of Colombia introducing our speaker today is very appropriate and very fitting. ARMA intends to serve the world by improving knowledge of rock mechanics and all the safety and efficiency that applies to in mining, in tunneling, and in oil and gas. And so it's very fitting that Juan is the host today. I think it's also very fitting to have Brent present. Dr. Slaker, he was an outstanding student, both as an undergraduate as well as a graduate student. And in addition to the project that he leads there at the Pittsburgh Research Center of NIOSH, he also cooperates with Nino's project that a number of you students are supported on. And so I appreciate him and Dr. Murphy's assistance with those projects, with that project as well. And so it's a privilege and an honor today to have Dr. Slaker present. And Juan, should I just turn it over to him so he can get started?
Yes, you can go ahead.
All right. Thank you, Brent.
Thank you for your words.
Okay. Well, yeah, thank you, Dr. Westman, for the intro. And thank you, Juan, as well, for setting this all up, for sure. And everybody else who's tuned in on a Friday afternoon, I'm sorry, I think I chose this time slot. But it wasn't sandwiched in with about 20 classes, so hopefully that counts for something. But yeah, what I really want to talk about today is our underground stone mining research that we're doing at NIOSH, really as a whole, from somewhat of a rock mechanics standpoint, but I understand there's probably going to be some people in here who are not rock mechanics experts, so it's going to be a little lighter. Hopefully that's okay. If you have any questions, feel free to interject at any point, turn your mic on and yell at me. I don't know if there's a chat feature in here. Hopefully something will pop up if you write in, but yeah, I don't mind if you interrupt. I might turn my camera off here in the meantime, because one, I'm working on a laptop, so I'm going to be real close to the camera while I squint to see some things if it's on. And I think I'm like much paler than everyone else here in the in the chat room. I don't think it's my lighting or not having gone outside enough. But if that causes problems, let me know. But okay, and now I can pace around my room. Who likes to give a presentation while seated? But to get started, for those of you that don't know who we are at NIOSH, I'm just going to give a quick rundown if I can figure out how to advance slides. There we go. We are really NIOSH Mining, I think, is the most common name for us. You might still use the name Bureau of Mines, which was replaced many years ago. Sometimes the Office of Mine Safety and Health Research. You might have heard us as the Pittsburgh Mining Research Division, which is one of the offices of the Office of Mine Safety and Health Research. Doesn't really matter. We go by a lot of names, but we're about 5 levels beneath the president there, sandwiched under NIOSH. What's important to know about us is we are not regulatory. We are a research arm of the government. So if you see there, MSHA branches off from the Department of Labor, not Health and Human Services. So the Mine Safety and Health Administration, the regulatory arm of the mining industry, is a separate entity. So even though we have a very similar name, not the same organization. So what we do at NIOSH, specifically at the Pittsburgh Mining Research Division, are a number of different minor health and safety research activities. I won't get into all of them because I'm already going to be talking for a long time, but feel free to peruse these slides later in the recording or the file that Juan sends out. But for the most part, it's behavioral studies, maybe lighting and dust studies, ground control studies, everything that affects the underground mine workers' health and safety. And here, just some more examples of some of the research we do at the Pittsburgh Mining Research Division. So ground control, what I work in, the ground control branch is one small part of what the organization as a whole does. But I like to think it's a very important part. So I'm going to talk about it for a while. Now, in our branch, we break into usually about 3 commodities in Pittsburgh, and that's coal, gas, and stone. So on the coal side of things at PMRD, we have ongoing right now a rib design methodology project where we're looking at underground coal mine rib stability. So what kind of support you might need for different ribs in different environments at different depths, different rib constituent parts, something like that, and how to design around that. Also, kind of a total entry stability assessment project as well, where we're looking at openings adjacent to active development, such as longwall panels and how those deform as that panel passes by. And from a gas well standpoint or gas well stability standpoint, we have a project looking at gas wells in the vicinity of retreat mining or longwall mining that might compromise the integrity of that well casing and cause gas to leak into the mines. So that's another big project we have going on, which is especially a problem in Pennsylvania, where we have so many gas wells and longwall mines at the same time in very close proximity to each other. So those are the other commodities. The one I'm working on is stone, which I'll get to in a second. But while we're still in this coal frame of mind, you may have also heard of some of our past research related to underground coal mining ground control in the forms of the software packages that have been put out throughout really the past, 20, 30 years. I know we learned ARMS in school there at Virginia Tech. We may have messed with ALPS a little bit. I don't know if we did a lot with ARBS and some of those other ground control toolbar software, but they all fall into the NIOSH umbrella or Bureau and then NIOSH umbrella. So if you've heard of those, that's who we are, people that made those. Now transitioning into stone mining, this is mostly what I work on. I can somewhat speak to that other research that's going on, but this is more my wheelhouse right now, is the underground stone industry. So if you're familiar with coal or metal, I'm just going to kind of contrast this with those industries. So with underground stone, we've got about 112 some odd mines underground stone mines in the country, depending on how you count them. And they're defined by, well, defined by being stone. But some of the characteristics that set them apart are their hard rock strength. So in the 80 to 150 megapascal range is usually the kind of strength you're seeing in an underground stone mine. You have prominent bedding. Usually have one or two prominent joint sets that are steeply dipping or faulting. You've got a room and pillar mining method where everything's laid out on a grid, either square, rectangular pillars. You've got pillar widths that go from 35 to 100 feet and pillar heights that go from 15 to 100 feet. So a wide variety of different pillar shapes and sizes. You don't have to deal with explosive atmospheres, so MSHA approvals and permissibility, things like that for the kind of technology you use inside of the stone mine, which is a great boon from a research perspective. You also tend to have mining that occurs on a front. So your front could be thousands of feet to miles long, where you have 20 to 30 active headings at any given time that you're blasting from. Well, probably blasting about 5 or so a shift, but you know, the large area that you're extracting, not just one small section. You've got mixed bolted and unbolted headings. So some mines bolt, some mines don't use roof bolts. Some mines use roof bolts sporadically wherever it's needed. Some have older workings that are unbolted and newer workings that are bolted. So it's really a mixed bag with what you'll find in underground stone. A lot of these mines have very old workings, so it's not uncommon to enter a mine and right at the portal, you're passing pillars that have been developed 60, 70 years ago. And really they become part of the structure of that whole mine because, you know, made decades ago, but it's still stability you have to worry about. And these are often in massive deposits. So you're not following like a 6-foot coal seam, something like that. You have maybe a 200-foot limestone bed, and you are benching different levels in there, opening up a whole new level. So you have a multiple level mine. It really gives you some operational flexibility that you wouldn't have in a narrow vein mine or a seam. So that's kind of what, to me, defines the industry as a whole. This is where these mines are located. Ignore the colors for now. We'll bounce back to the slide in a second. But you see the eastern half of the U.S. is where you find most of these underground stone mines. I think your local mine there, Kimballton, should show up as a green dot in Southwest Virginia. If you know of any other Virginia underground limestone mines, let me know. But it should be all of them. So that's the industry. Now, what does this have to do with our research right now? About, I'm losing track of years now, we'll say 15 to 20 years ago, we had a pretty big underground stone research effort at NIOSH. I think largely this was led by S.C. Esterhazy, Tony Anacchione, Dennis DeLeaner. People like that were researching a lot of the underground stone problems that existed at the time. And out of this, they developed a tool called S-Pillar, which you might recognize a lot of the input parameters from programs like ARMS, where you put in pillar dimensions, so widths, heights, your material properties, the rock strength, depth, all these different parameters that you would need to design pillars that remain stable in underground mine workings. So that's what it's for, is plugging in your mine parameters, and it gives you a design chart that tells you if your pillar is going to be likely stable, or we can't say that it's probably going to be stable. That's what S-Pillar gives you. So this is a software that helps you design underground stone pillars, which is great. This is kind of where we left it for maybe 10 to 15 years. And now we've come back because S-Pillar was designed really for mines that are fairly shallow, flat-lying, single level, not dipping, which does encompass most of the industry, or at least about half of the industry. At the time, it encompassed a little bit more. But what we think is happening is more and more mines are going into multiple levels or mining deposits that are dipping. or maybe getting deeper. And maybe that we can't apply the equations and the software that came out of that old research to these new environments. So right now we're doing some fundamental research to try and understand what makes those situations different, and can we use the software? Can we use these underlying equations in those environments? Or do we have to come up with some new way of thinking of how to design mines in those challenging environments? So when I say challenging, I tend to mean mines that are dipping significantly, mines that are multiple levels, or mines that are very deep. Now, if I right back up to this map, now the colors might make a little bit of sense. So everything in green right now, every green dot is a mine that we know is in some condition that we would consider challenging. So it has some significant dip. It's very deep. It's got multiple levels. Everything in red is a mine we don't know anything about. And a mine of black here is a mine that we know is probably in a situation where S-pillar could be applied to most of the pillars there. So just judging from this, you can see that probably about half the industry could use some enhanced recommendations or guidelines from this research. So we've got a target audience here. So that's who we're trying to reach. Now, what do we do about it? And now I'm going to kind of walk through the research process, our thinking, and all this. And this is where you're free to poke holes in it or ask questions if you want. But we're starting from a place of how do you determine the strength of a pillar? That's really what we're after. Is this pillar going to remain stable? How strong is it? So I usually hate to put equations into a slide or into a presentation. So just kind of gloss over them. The important thing out of these is the height component. So here we have right now Headley and Grant hard rock pillar equation. It's kind of the grandfather of hard rock pillar equations. We got another one. I'm just kind of cherry picking hard rock pillar equations here. Lunder and Picalnus, this one goes down a couple levels deep, but ultimately does boil down to a width and a height component. The one that S.E. Esterhazy developed for underground stone mines, also very dependent on that width and height of a pillar, which, that makes sense. That your pillar strength would be some function of the width and height of a pillar. I think we can all agree on that. All the experts have agreed on that throughout time. But the problem for us comes in with quantifying that height component when your pillar is dipping. And also when your pillar is multi-level, but we won't get into that for now. When your pillar is dipping, how tall is it? So in fairness to the first couple equations here, they were developed based on pillars in the Canadian Shield, which I think are pretty much all dipping significantly. But regardless, we want to figure out what number to plug into these equations, or if they still apply when you've got some kind of differential height. So imagine for a minute a dipping mine. So you've got a room and pillar layout, just pictured as a massive grid of squares or rectangles. And now we're putting this into a dipping deposit. So your pillars are, if you just take a flat mine and you dip it down, your pillars are going to look like that middle image there. Do I have a laser pointer? Oh, you can see my mouse probably. That middle image is a dipping pillar. So obviously you're not going to mine a pillar where the rib is angled and hanging over you. So operationally, that's not what it's going to look like. So that height really is not that meaningful there. So let's jump over to the right side. You could mine a pillar like that in a shallow dip, or if you had equipment that could get up that kind of incline. But at that point, what is the height? Is it the length of either of those sides? Because the top side there, top right and the bottom left, are somewhat confined on one edge. So can we still consider this to be the same height that these other pillar equations are looking for? Or take the left image, in an instance where you want to work on a flat floor. You don't want your equipment always tilted to one side. Now you've got a short height of a pillar and you've got a tall height of a pillar. Do we average them? I don't know. That's the question really that we're after, is is what is that height? Now that's one question, I should say, is how to plug that into a pillar strength equation. We also have an issue where there are different stress concentrations on the up dip corner of an opening and the down dip floor corner of an opening. We've got stresses that are not symmetrical across these pillars. That's another issue. But just at its simplest level, there are reasons that we can't apply our past understanding to this environment. So that's dipping. Now let's take a look at multi-level. Now, here's my quarantine special analogy. So you've been hoarding toilet paper, probably like everybody, and you bought a yardstick from Amazon so that you can hold it out in front of you and keep people 6 feet away. Okay, so you've got these tools on hand. If you set these up as shown, where you've got offset toilet paper rolls around a yardstick, and you stand on top of those top 2 toilet paper rolls, you're probably going to break your yardstick. If you don't, get your roommate on your shoulders, still stand on it, you'll probably break that yardstick. If not, it'll bend significantly. The point is, there's some kind of loading there that could break that intermediate layer. If you stacked those rolls of toilet paper on top of one another, you wouldn't get that. That yardstick would survive, many more roommates on your shoulders. So there's an issue here with the load transfer from the top roll of toilet papers to the bottom. So now in a multi-level mine, we've got the same thing. Those top rolls of toilet paper, just pillars, same with the bottom. There's some thickness of rock that can exist between levels of a mine where that stress from the top level pillars is going to cause some kind of failure in the interburden as it wraps through it to transfer that load to the bottom level. We don't know what that thickness is. There are some rules of thumb. There's some research from the coal industry that would suggest it. But right now, we really don't know what that is, and we don't know the significance of that interaction between levels. Because you're also, once again, asymmetrically loading these, well, in this case, toilet paper rolls. One side of these rolls might be higher loaded than the other, depending on where the pillar above it is placed. So that's the problem there. And I think this is one of the places we can make a huge impact with this research, because right now it really is just kind of guessing. We see a lot of mines that just keep going until there's a failure. And I mean, that's one way to mine. It's a way we've mined for thousands of years, probably. But we're hoping to improve that a little bit. So real quick, just how we're conducting this research. We've got a research question. How much interburden rock do you need between levels of a mine? So from there, we go to the actual research itself. And I remember from graduate school, and I'm sure Dr. Westman will as well, hearing, you've got numerical modeling, you got lab studies, you got field studies. A good research project should probably have at least 2 of those. And I really understand now that a lot of that comes from a place of trust and validating the findings that you've come across over the course of this research. Because I can't tell you how many numerical models I've seen now where it's like, yeah, I understand the results you're getting, but I don't trust they're real because I think you put garbage into your input parameters, or I think you're tweaking something I don't understand and you haven't validated it against a field study, or you haven't validated it against something I understand in the lab. So I'm just going to throw out everything you presented to me. So I think it's important to build that trust, which is something we're going to do here in the form of field studies that validate our numerical models. And that's pretty much just what I said here. Communicating those findings, it doesn't matter how great your model is if no one believes it. And I firmly believe people are inherently very skeptical of numerical models. So that being said, let's tie that into our instruments. So I'm going to go over some instrumentation that we're using at our field sites right now, and how we've been successful and unsuccessful with them. I'm sure if you've taken Mario's instrumentation class, I don't know if he still teaches it, but he did when I was there. You probably learned about a number of different methods of calculating stress, displacement, and other rock responses to loading. But for us, we stuck with the vibrating wire biaxial stress meters for our stress monitoring. And this is just think of it as a metal cylinder that we insert into a hole in the rock and grout it in place. And then as that that rock or that pillar, in our instance, takes load, it's going to compress the cylinder. And as the cylinder compresses, there are wires inside of it that are going to shorten. And as they shorten, the frequency across them changes. And as that frequency changes, we can start to infer, based on the properties of the rock and the properties of the cylinder, what kind of stress we're seeing in the rock. So that's really what these do. And they tell us that stress in two axes, or really a plane, we can get the principal stresses. To complement this, we also have a seismic monitoring program at some of our case study sites. We use Uniaxial accelerometers, and we have one Triaxial accelerometer installed. But for the most part, these pick up microseismic activity that occurs in the rock. So as rock breaks, it creates some energy that travels through the rock, and we pick up that signal as it hits our accelerometer. And when it arrives, at each sensor, we can use to triangulate where the event happened. So we can start to watch events happening in certain places and infer, oh, there's damage occurring there. Why is it occurring there? And then take that further into our fundamental understanding of why the rock is breaking. And probably the last instrument I think I'm going to talk about is LiDAR. And I'm sure, I don't know who's in the video right now, but if there's a seminar, you've probably seen Juan and Richard talk about this a good bit, but we are also using LiDAR for ground monitoring. So you'll usually see this in a tripod-based or vehicle-mounted manner underground. We do most of ours with the tripod, but we do have one site where we mount something onto a truck to scan. But for the most part, this just shoots a laser into a rotating mirror. We measure the time it takes that laser to bounce from the origin to the mirror to the rock and back. Using the speed of light, we can calculate how far away it is. So that's how it works, and it produces a nice geometry of the mine. So this is going to be our first case study site. But you can see we get a lot of detail from this LiDAR. And this is, my favorite technology that we use. So I'm going to spend a little bit more time on it because I have you here as a captive audience. This slide shows some of the applications of LiDAR, or really, it's distance measurements you would want underground, most of which you could get with LiDAR. Now, I made up every number on here just based on my experience, so you can argue with me on it. Especially, I'm sure surveyors would argue on what is that, 5 centimeter precision. But let's say you want, if we're looking at how to read this, let's say you want roof convergence. Hard rock breaks after very little deflection. So over the span of an opening, that could be several centimeters. So if your rock is going to break after several centimeters, you're probably going to need several millimeters of precision to watch it bend before it breaks. So that's where you're seeing some of these precisions. Or if you want mine geometry, if you just want a basic structure of what your mine looks like underground, you don't have to be precise. You probably just need a few hundred points per break. So that's where I'm getting a lot of this information. But yeah, look at it at your leisure and argue with me later. But with this LiDAR, what we're mostly using it for is geotechnical assessments. So we're measuring joint faces for their orientation. We're doing elevation contours, which is really just coloring it by height, which sounds simple, but it's actually the thing that probably makes people the happiest when we show the mine some of our process data, and we'll show you why in a minute. And the last one, which is probably my favorite, is change detection. So if you scan something multiple times, I scan it 1 month, then I go back the next month, and I just see how that geometry changed. Where it changed can tell us a lot about that rock and its loading. So I'll show you some examples of that as well. But that's our instrumentation. So real quick, I'm just going to touch on our numerical modeling as well, because this is a big component of what we do and what's going to inform our research after our instrumentations are done. But we use mostly FLAG 3D at NIOSH. That's what you're seeing here in these pictures, actually. We dabble in some other software, but for the most part, we're using FLAG 3D on this project. But the way this numerical modeling software works, if you're not familiar, you build out the geometry of some structure, you input the properties of that structure, so strength, cohesion, friction angle, these kind of things into the rock. You excavate, so you create voids, and then you watch how it deforms around that, where stresses go, what loads differently than something else. So that's how we're using that. And you can see here on the right, you excavate that opening, and you see some deflection of the roof into the opening. And we can use this to create situations that we don't actually observe underground, that we aren't able to observe underground.
Hi, Brent. This is Aman. I would like to interject. We got a question on chat from Christian.
There is a chat?
Yeah. I could ask it for you.
Sure.
So it says, hi, Brent. How much does NIOSH rely on numerical modeling tools? Could you possibly share your thoughts on how useful this might be? And have NIOSH used UAVs for digital mapping or not? So there are two questions.
So yeah, let me answer those one at a time. I can't speak on behalf of all NIOSH, but I can say at the ground control branch in the Pittsburgh Mining Research Division, we rely on numerical modeling a lot. Probably about half of our scientists in the branch have got some level of modeling expertise, from world expert to intermediate, and I think it's because even though we're able to access a lot of mines, you just are not able to instrument every possible condition that you'd ever encounter. So we really do create models probably nonstop. We've got parametric studies running at any given time that occupy probably 6 or 7 workstations at our office. So I would say significantly is how much we're relying on these numerical models. And for this project, also, every recommendation we make is going to go through a parametric modeling analysis, where we're looking at different mine dips, different width to height ratios, different strengths, different stresses, different stress orientations, because we just can't instrument all these environments. So we use it a lot now, and we're going to use it a lot going forward. It's probably more useful to us than the instrumentation, if I'm being frank. And as far as UAVs are concerned, I know we've recently started dabbling in importing geometry you obtain from like LiDAR into these modeling programs. Run into issues where very small elements cause anomalous behavior in the model, so we'd end up having to simplify them a lot to where you're not getting a ton of benefit out of the density of LiDAR scans. But I would say, yes, we're starting to do that. And actually some of our models I'm going to show you here do come from LiDAR data. But that's the only way we're really interfacing those two things. We use we don't use UAVs, but we use similar data you would obtain from UAVs for other analyses, but not really with the modeling. But yeah, Aman, just interject at any point if there's a question. You have my permission to to yell at me, because I don't know how you're all seeing the chat. But
don't worry, Brandon, we can see it.
Okay. Okay, well, that was a great point or place to interject, because yeah, we're transitioning into case studies here, and I'm not going to name them. Hopefully, I might accidentally name some of these mines, except on the right, the Subtropolis quarry. That one they gave us permission to talk about whenever we want. But we'll start with this mine here on the left. This is a dipping. This is a dipping mine, and it's in central Pennsylvania. And remember earlier I said that a lot of these mines you might enter past some old workings. And you can really see that reflected on this mine map. If you get in closely, up towards the top left is where the portals are. And you can see a lot of odd pillar shapes and orientations because they were mined many decades ago. In fact, fun anecdote about these pillars, the way they designed these, they didn't know how to run a pillar strength analysis to determine if it's going to support the overburden. So what they did was they made a large pillar, incredibly large, hundreds of feet on a side, and they just started, they cut it in half. Did it stay up? Great. They'd cut it in half again. So now they've quartered the pillar. Did it stay up? Great. And they just repeat this process until the pillar started failing. So this is, it worked, I guess. They were able to continue mining, but this is the process that they were using for designing pillars decades ago. So I like to think that we're a little further along than that now. But where we are now for our instrumentation is in this area kind of on the southeast. So that's a blown up version of our instrumentation area. And our goal here is to instrument a pillar and watch it behave as it gets mined around. So remember, this is a dipping mine. So in this area, it's about probably an 18-degree dip, and it's dipping to the southeast. So the dip is so steep that the crosscuts have to come off of it at an angle to create an apparent dip that is low enough for the equipment to traverse the slope. So that's one of the complications that gets introduced with these dipping mines. We also have here a high horizontal stress environment, which creates a different problem. So you see there that sigma H is our major horizontal stress direction. I think the magnitude's around 32 megapascals. And that's going to create its own problems that I'll show you in a minute. But that's kind of the site setup. And again, this green dot shows the pillar that we instrumented before they mined around it. So if we're going to see the loading on this pillar, we need to get instruments in before the loading occurs. So that right here is when one rib is exposed, which, if you recall, the mining method here is going to be drill and blast because it's a limestone mine, and there's active workings all around us. So logistical nightmare incoming. Here's a picture to help you visualize that, especially if you don't spend a lot of time in underground limestone mines. You can really see the dip there of the crosscut on the left, and the headings they're gently dipping towards us in this picture, maybe a couple degrees, but for the most part, they're flat. And here's another laser scan cross section to help you visualize that dip. So the horizontal stress, as I mentioned, was causing a few problems, namely in the form of cutter roof failure. So this is one of the headings, and you can see up above where that man basket is, the roof has peeled off. Some of the roof bolts are hanging there, and this is the leading corner of these headings is what they're sitting under right now. So as that leading heading pokes out into the stress field, that corner gets hit very hard in the roof and breaks that rock. It also gets hit on the up dip side once that heading's gone out a little ways, because on the up dip side, the compressional forces can crush it. So it causes a lot of problems. So where we put our instrumentation is outlined on this map. All the yellow squares are laser scan locations when we went in the first time. So we established a baseline laser scan that we can compare every future laser scan to. And I'm going to bounce between LiDAR and laser scan, so bear with me. We've got seismic sensors set up all over the place, uniaxial accelerometers at different heights and orientations. And we have those biaxial stress meters that I mentioned installed in this pillar. So we're using all this instrumentation, and we just want to get an idea of what is happening around this pillar as it gets mined. So you see the dotted lines there show the projected development into the future. They're actually still mining this. This image is 3 years old, I think, and they still haven't completed mining around this pillar. So like everything I show you today, this is a work in progress, and I apologize for that, but hey, at least you get to see the research process. Here's another image of us really in that cutter roof area, but this is installing the seismic cable. Again, logistical nightmare because of the blasting in proximity to all these instruments and the cabling. But those elevation contours I mentioned earlier with the LiDAR data, this is an example of those. So this here is just, again, coloring based on height. So we can really pick out where those bedding planes are. If you go in there and just see, where has the rock peeled to? Okay, this is the new bedding plane height. And do this, and you can just create a map for a short section of the mine that shows where your bedding planes are located. What we found through this, actually, that wasn't intended, was that roof falls make for excellent places to characterize joints. If you're just looking at a point cloud, or if you're a geologist on the ground, going through an underground mine, and you're trying to find nice fracture planes to record and make a stereo net out of, you've got to deal with a lot of mess. Blast fracturing. But when you're dealing with a roof fall, things tend to fall out along these pre-existing discontinuous planes, and you can find them in the laser scan. You're probably not going to get a man lift and stick your geologist up into a roof fall because it's inherently unstable. But you would do it in a laser scan. You could set up your scanner under it and then just kind of back up a little bit and let it go. So huge benefit of this technology we didn't anticipate. Here's another elevation contour map. And I'm sorry if you hear my kid screaming in the background, but telework life. This is another contour map of elevation, and this is showing everything in red is above the average roof line. So that really helps to highlight where this cut or roof failure is happening. So you can see in all the crosscuts, for example, which are in an unfavorable orientation relative to the horizontal stress, that leading corner is pretty red because it's just getting crushed by that major horizontal stress. And you see it's on the same side everywhere but that top crosscut, the very top middle of this figure, where it's on the other side because that crosscut was driven north. So fundamentally it lines up great with what we'd expect. And you kind of see it on both sides of the headings, and that's because that top side of the opening gets crushed from the horizontal stress, and the leading corner of the heading gets hit with the horizontal stress. So these are really nice to see, and we can quantify the damage. We can measure the volume of rock that's come out of the crosscuts versus the headings. So that's the elevation contours. Now, if I jump to the change detection stuff, which is my favorite, we've really got spalling probably is the easiest thing you can identify here. And the reason we do this is because if a rock mass is taking load, we expect there to be some kind of damage associated with that, to shed rock off the side for material to spall or slough off. And this also happens at magnitudes that you see here, 55 centimeters. It's usually tens of centimeters, sometimes hundreds of centimeters if it's a significant pillar stress event. And any LiDAR scanner is going to pick this up. Even if it's a poorly registered point cloud, it's going to pick this up. So that's why we love using this information to draw conclusions. But kind of the holy grail of change detection is seeing that rock deform, kind of dilate out or converge down or heave up without breaking. And we were able to see some of that in this mine as well. So this is a plan view of a section of roof that we see converging. And this black here tops out at 6 centimeters. So 6 centimeters of deflection in a roof, hard rock roof, is a lot. And we're able to see that develop in this mine with these periodic LiDAR scans. So really nice to see. But what's interesting about this too is the location of it. It's not centered in an intersection. It's offset, which is a little odd. I think typically you kind of think the middle of that intersection is going to be where you see most of your deflection. So keep that in the back of your mind for a couple slides. Because I'm just going to roll through our instrumentation and what we're seeing with it. We also, remember, had the Stressmeters installed. So they started mining down the left side there. If you're looking at these projections, they mined the left crosscut first. So one of those stress meters showed a significant uptick in stress as soon as it was mined adjacent to. What we didn't see or didn't expect, and this is going to turn into a lessons learned lecture, I feel like, was the impact of that horizontal stress relief on our instruments. So if you recall, I said there was a high horizontal stress environment here. We installed these stress meters into a pillar that was experiencing high horizontal stress. Then we mined adjacent to it and we relieved some of that horizontal stress. Well, now we've got a concern where maybe the grout is going to decouple from our instrument, or the rock is going to decouple from our grout, something along those lines, and then we won't get good measurements anymore. So that made it our interpretation of these results a little, just a little uncertain. But we did certainly see change with each blast, which is good. And we're still processing this data, so I'm not going to give you a good answer for what we saw in the loading. But just to give you an idea of what this data looks like in practice. And last instruments we had installed, Seismic. We caught a lot of microseismicity associated with blasting, really near that highly stressed corner of the excavation, but we didn't see a lot inside the pillar we were monitoring, which is where we kind of thought we would see some, but I think we just assumed that there's not enough loading on that pillar and actually some unloading, if you think of the horizontal stress, that maybe we just wouldn't see the seismicity associated with rock fracture. And the last thing I want to talk about at this site is our numerical modeling. So we modeled based on the geometry from the laser scan. You see it's not, it doesn't look like it's LiDAR geometry, but if you look at the Z axis on this, all the heights and widths really are taken from an average of points in the LiDAR scan. So we modeled each blast. So you excavate 12, 13 feet, let the model run to equilibrium, excavate another 12, 13 feet, do that. And what we found when we got to this intersection where we saw that roof sag is a sag biased towards that side. So it must be some function of either this crosscut orientation or the stresses or the dip. So there's something about this specific mine geometry that does reinforce what we saw in the field and the models. So we're still, again, in the process of tying all this together, but to give you an idea of how we're validating our models of what we're seeing in the field. Our next case study is going to include 2 mines. So we'll just move straight on into those, and Aman will yell at me if there's questions about the other mine, but this is our multiple level mine case studies. So a lot of mines, again, in these large deposits, maybe hundreds of feet thick. So you mine out your top level. You say, hey, well, we hit our property boundary. Let's just open up another level below it, and maybe another one below that. So you might end up with these multiple level mines. Our first mine, well, I'll just describe the mines before I get to that. Our first mine is a thin interburden mine case where that distance between the levels is 20 feet. Our second mine, same kind of situation. You got a top level. Let's open up another level below it, 85 feet. So, about 4 times as thick an interburden. And those are the 2 case studies we're going to compare. So what's the problem? Well, as I mentioned earlier in our toilet paper analogy, when we've got pillars that are not stacked, you tend to have these stresses have to wrap through the interburden and can cause a failure. So in short, that's what that says. And we just want to figure out how close they have to be before that's a problem. So you see that thin interburden case on the left, our thick interburden case on the right. You see our pillars are stacked on top of each other on the case on the left with the thin interburden. They are not stacked on top of each other in our case on the right. So first case, the thin interburden, the one on the left, we have the similar setup to the first case study with the dipping mine. We've got stress instrumentation, seismic instrumentation. We've got our LiDAR scans, and we just kind of scatter it around the area to get a picture of where stresses are going everywhere. So yeah, that involves drilling into the interburden. Here's just an action shot so you can put yourself in the scene. And because these pillars are stacked, we expect stress to transfer pretty well through the levels for there not to be a big change. Because if you think about it, when you're mining underneath of an existing level and you stack your pillars, the rock you're removing should not be supporting that much weight because there's not a pillar directly above it. So there shouldn't be stress transferring through that. So we don't expect a lot of change. And that's pretty much what we're seeing here. That scale is negative 0.25 megapascals to 1 megapascal. So it's not a lot of stress movement we're seeing. What we are seeing is, I said they were stacked, but just because you try to stack a pillar doesn't mean you perfectly stack a pillar. So we find that when some of these corners overhang, we get a significant amount of pillar spalling. And that's what you're seeing here on the left, is progressive spalling of these corners of the pillar where it just was not perfectly stacked. So you see some elevated stress concentrations. On the right, this is just neat because I like LiDAR data. We actually saw the rock kind of moving out a little bit. So we scanned it a few months later, it had moved out. And then a few months after that, it had fallen. So just an example of tracking the rock, either becoming loose or dilating. And our seismic data here, this is a very old figure, but for the most part, we're seeing events scattered around the study area. But if you take the average of those, they do tend to coalesce around active productions. And we're hoping to see these preferentially in certain places around the interburden and pillars. Now the other mine, similar situation. Remember, top level mined, bottom level coming under it. We did not mess with seismic instrumentation here, mostly because of the cost and the people. We didn't have them. We didn't have the money. So we just did stress meters and LiDAR data. So you see here where we put stress meters in a pillar before it was undermined. And the idea is if you have a pillar on the top level that is sitting over what will become a void in the future on the bottom level, the stress should drop wherever that void is created underneath it, if there was an interaction. So we put stress meters in these places that should experience stress drops, some places that should experience stress increases, and we're just going to watch them as they undermine, see what happens. Now remember, this is very thick, so there shouldn't be a lot of interaction. So we modeled here their case, where it's 85 feet between the levels, and we should see these stress meters move tens of kilopascals, nothing, essentially. But if there is some interaction, we did an example where we modeled in FLAC 3D an interburden half as thick as what they have. And at that thickness, you see stress changes on the order of several megapascals. So we're expecting to be somewhere in that, between those two conditions. I guess hopefully we see no interaction, but that's why we do the research, to turn that from hopefully into a definitive. And the last case study, last mine, then I can turn everybody loose. We've got the Subtropolis mine, the one I can name. And this is in eastern Ohio. It's not the traditional challenging in the sense that I defined it earlier. It's challenging in the sense that everything's going wrong. You've got high horizontal stresses. You've got coal measured rocks all around this. The deposit's about 20 to 22 feet thick. It's sandwiched between shale and sandstone. There's some coal mixed in there. And you're operating on thin margins. You only have so many control measures you can take. So here's a picture of it. And you can see a nice roof fall running down the middle of this opening. The bolts hanging out there. It looks pretty gnarly. So this is, I want to say it's atypical, but it's really not. You see this kind of thing all over the mine. And here's what that mine looks like. So they started out, well, a few years ago, they were mining what they thought was in the direction of the major horizontal stress. But after a number of falls, reassessed where we thought that stress was, we turned the mine into a new direction, which now is kind of northwest, northwest, around that direction. And the idea is, if we're driving directly into the major horizontal stress, the heading should be okay. The crosscuts will get hammered and just experience a ton of damage. And we'll just protect the crosscuts. Do whatever we can to protect the crosscuts, and at least then we don't have damage everywhere. So that's what we're trying to do here. And here's an example of those falls. So you can see these roof falls here that these couple NIOSH researchers are looking at. exist all over the mine. There are entire sections of the mine that are just cut off because these falls have occurred. Here's, yeah, thousands of feet away from that other fall is another one. So completely block off access to that area. We're trying to prevent this from happening because you start to lose access to reserves, and it could mean the end of the mine. So what do we do? Now in this new orientation, we expect our crosscuts to get hammered. Now we've got an engineering problem where, let's go down the list of easiest solution to this problem. And I feel like we're on number 19 or 20 right now. But just hitting some high points, bolting, you think increase your bolting. Well, again, we're operating on such small margins that we can't just double the bolting throughout the mine. But here's, if you're interested, the kind of bolting they're doing right now. Can we increase the distance between our crosscuts? Essentially reducing the number of crosscuts. Well, if you look at this map, the portals are on the bottom right. Our new development is in the top left. So ventilation is a huge concern where they are right now. They just can't get enough air to the section to increase the distance between crosscuts. Angling crosscuts, they tried that. Wasn't very effective, didn't seem to improve the situation much, and it caused a haulage issue. Can we offset our crosscuts so that when these falls occur, they don't just run through the mine? Well, the problem is they still snake their way through the mine when they did this, and also it created a haulage nightmare again. So right now we've gotten to the point where we've settled on these things called windows, where we essentially just drop the roof down a few feet, about 5 to 6 feet in this case, and we create a thicker roof beam there that hopefully will not break from this high horizontal stress. And for the most part, that works. So how do we know it works? Well, this is where, again, these elevation contour maps that are so simple yet so effective at understanding how roof falls are making their way through mines, where they come in handy. So you see all these red spots in here are, again, places above the average roof line. So you can see where some of these falls are just snaking around crosscuts. And what we're looking for here is a lessening of damage after they turn it into the new orientation to show that it's working. So less red, which I think for the most part we are seeing. But if I zoom in on one of those areas, you can see how one of those roof falls, they start in these crosscuts, they just start snaking their way through the mine, but they don't go through these windows. So the mine has adopted a lot of these windows. We've been studying them, and they're just putting them in as regular practice now to try and prevent this from happening. So that's how we're using that technology there. But I should say this LiDAR, I've showed you a huge area, but I didn't tell you that this is where we use that vehicle mounted LiDAR. So before, everything we did was with our tripod mounted one that I showed earlier. This, we actually contracted someone out with a LiDAR scanner on a vehicle to process this data for us. And we did it many times, and we're hoping to see some kind of change detection as well. So that pretty much wraps up everything we're doing right now with this underground stone research. But just to recap real quick, the things that worked well for us, this LiDAR, it's the future and the past at this point as well, but still the future. Numerical modeling, obviously used widely throughout the industry. It's working great for us, but the problem is finding those cases where we can show what we've modeled underground without just tweaking the models, until they show it. Showing like legitimately, reinforced models. We can justify all the parameters in them until they show what we're seeing underground. Things we've learned, the lessons learned lecture. Our instruments probably too close to blasting in a few scenarios. Seismic array tended not to be the perfect solution to understanding stress and fracturing in the rock. When you're at such close proximity to your events, you have problems picking out P&S wave arrivals, you have equipment getting damaged. It's hard to get a good orientation of your sensor relative to where the event's occurring. So some problems there, but from here, I think, we've got all these field studies, we've got all this instrumentation data, we've got these modeling programs going on, and you just tie them all together. And at that point, once we tie them together, we improve the models with the field, and we expand those models into parametric studies that test different, different interburden thicknesses, different width to height ratios, that kind of thing. Then we can start to make broad stroke generalizations and recommendations for the industry. So everything I put in here is stolen from various publications and presentations throughout the years. You can find them here if you're interested, for your reference in the future. And I have to read this, so bear with me. The findings and conclusions in this presentation are those of the author and do not necessarily represent the official position of the National Institute for Occupational Safety and Health, Centers for Disease Control and Prevention. Mention of any company or product does not constitute endorsement by NIOSH. So, thank you for bearing through that. NIOSH will not stand by anything I said. But that about wraps up our current underground stone research. So, thank you for listening and sticking around. I know I took us to 4. I was probably supposed to stop a little bit earlier, but I'm going to blame Aman. So if there's any questions, just hit me. I'm around all day, so you're not holding me up.
Thank you very much, Brent. I think it was a very, very nice and illustrative presentation on what you guys are doing right now with these challenging mines. So yeah, I think if anybody from the public would like to ask additional questions, I think, I don't know, how are you on time? Maybe you'd like to answer a few of them?
Sure.
Hi, Brent. Thank you for such an insightful presentation. I have one question to ask you. So sure. When you take on a project do you limit yourself to working on it for just numerical modeling, or there are projects where you have to work with the ventilation department, work with the safety department, work with the working out the laws and how much you can make the changes? So how does it go?
Well, I guess that's kind of a 2-part question. The first one is, I think our gas well project actually is an excellent example of how we do some of this cross-disciplinary work. So that one, you've got a ground control issue where you're subsiding the earth from this retreat mining or longwall mining, compromising these well casings, and you've got a ventilation issue because you have this gas intrusion that might result from a compromised gas well. And then where does that gas go? And we need to measure permeabilities and things like that right now that honestly as ground control engineers, we're just not as equipped to do. So that's one area where we would bring in that cross discipline. And then when you're actually at the mine as well, working with them, I mean, it's rare that you find a ground control engineer specifically to work with. Usually a mine's got an engineer or 2 or 3, but they're general engineers, and everything you say has got some implications, especially in Subtropolis. The consequences of one ground control solution opens up a ventilation can of worms almost every time, or opens up some cost concern that we don't think about as a ground control researcher. So really that just has to happen, I think, in the field is the problem. That's why it's so important, I think, to have those field studies and those contacts with the actual mine engineers, because they'll tell you what designs you have that are going to cause them problems elsewhere and they're going to ignore. But yeah, I don't know if that answers your question or not.
Yes. Thank you very much.
Hey, Brent, I had a quick question as well, and also wanted to thank you for the excellent presentation. I enjoyed it. Was really just looking for some feedback on that mobile-based LiDAR system.
Yes.
Does it meet the needs that you would typically have to scan a pillar, or did it leave more to be desired? What's your view on the ability to use maybe even a less expensive LiDAR system and cover more areas of the mine? Would you still be able to do the geotechnical analysis that you were doing with the Pharaoh's 3D scanner, for example?
Good question. So actually, a few hours ago, I was answering a question for somebody else, because we're writing a paper about that LiDAR scanning at that mine for the International Conference on Ground Control and Mining. And they used 2 scanners as part of this, because we did 6 separate scans on different dates. One of them collected at about 6 times the rate of the other. But we called them kind of comparable because when we get that data, we downsample it significantly. So we'll get millions of points per 100 meters. And we just can't process that much data. And that's from the sparsest LiDAR scanner we get. So when it comes to the quantity of data, it seems like almost any scanner out there is sufficient. It's really the precision of that data that matters more when you're looking at these engineering measurements. And I think that's true for almost everything, but then you mentioned geotechnical. And the problem with that, I think, especially when you're going with, let's say, tripod-mounted scanners or a line scanner that's moving linearly, is that you get these situations where a fracture plane is oriented, let's say, facing the scanner. And it's just hard to get enough points on that fracture plane to quantify it. If you end up with 2 or 3 points on a plane, it's going to be pretty hard to have any confidence in that. So I'd say with that, yeah, you need as high a precision as you can get. For us, what we found is that this is high enough. What we've seen with this mobile LiDAR, and it's I think the rate I saw earlier was 40,000 points per second. And theirs, I believe, was a line LiDAR that advances linearly down an opening. But I think 40,000, I haven't done the math, but I think that seems pretty typical.
Quick question. I know you've done a lot of work in photogrammetry, including underground photogrammetry. Do you still do that, particularly in underground stone mines, or have you and the rest of NIOSH really just moved right over to laser scanning?
About an hour and a half ago, I deleted the photogrammetry slide I had out of the presentation because I thought I'd go too long, which I think I did. But we did some photogrammetry at the Subtropolis mine, that last one, a few years ago to look at floor heave. It was mostly because we didn't have a laser scanner at the time. And what we found in the process of doing all that is because we were doing it with a DSLR camera. By hand, and then using, at the time it was Agisoft PhotoScan, forgot what it's called now,
Metashape.
but Metashape, that's right. The problem was to do, let's say, from one crosscut to another crosscut. So about 100 feet, 80 to 100 feet, we might need 30, 40 pictures in that area, and we had to bring in some auxiliary lighting just because of the size of the openings, that it was just very time intensive. And we also found that some of the structures, let's say there was a puddle or something, that it would just create these blank spots in our model as we reconstructed it, and the quality of data from there just didn't look as nice, and it took a long time to produce. But the precision was very high. We were happy with it. We did see floor heave, which was our goal in that research endeavor. And I think it did that as well as laser scanning could. And obviously it has applications in places where you need color, for example. But I think it's just as valuable as photogrammetry or as laser scanning. And I see it a lot on these vehicle-mounted systems that need to locate or orient themselves in 3D space. The problem for us, again, it's just it takes a very long time when you're dealing with these large void spaces that you see in underground stone. I've used it in coal in the past. I think it works better than LiDAR because with such a small opening height, you have to leapfrog a scanner a lot. But yeah, and the lighting, I think in a number of photos becomes an issue in stone for land-based. If you're on a drone, I can't speak to that so much.
Yeah, I think we definitely concur with you in a lot of our experience, particularly stone. Yeah. Thank you. Appreciate it.
That's good to know.
Brent, I think I have a question. So where do you think or this project is going, or what do you think will be like the result from this overall project? Do you think that the idea is kind of like generating similar guidelines than the ones you generated previously for flatline deposits? Do you think you're gonna come up with an empirical equation, or do you think it is more of like recommendations on how companies should start using laser scanning or photogrammetry, or what do you think will be the product for all this, like for companies to be able to implement all these greater results you are being able to obtain, right?
Good question. That's the question. I think that in a perfect world, the outcome is we say you can use S-pillar in these situations. You're at this thickness, just use S-pillar. You're at this dip, just use S-pillar. We don't anticipate that's going to happen. It seems like there's very clearly a critical dip in thickness where you start to run into issues. And we actually have a paper was going to ARMA this year. I think it still is, but it will be in some, whatever the ARMA format is, where we looked at different interburden thicknesses relative to different pillar overlaps. And out of that, we have a number of design charts where you've got, let's say, pillar overlap is 70%, interburden thickness is 4 meters, depth is this depth. And you just kind of follow your mine, and based on our parametric modeling studies, it tells you how much of the interburden zones in the models we expect to fail. So that's where we're at now. So we haven't yet figured out what's an acceptable number of failing elements. How do these different parameters interact with one another? Because now we're varying one at a time in the parametric study and showing design charts for one at a time. We're not sure how many of these variables we can lump together. We have to do some sensitivity analyses on that. But I imagine in the near term, design charts are probably the most practical application or practical outcome from this, as well as general guidelines about where you're going to see stress concentrations in these environments broadly. Yeah, as far as an equation, it has to account for everything essentially in those design charts. So it's hard to say how difficult that will be. But yeah, I think in the short term, probably those design charts.
And I think that something that could be also very useful for you to maybe like include or maybe to add to software like S-pillar, maybe to also consider for these design charts is maybe the possibility for the engineer or the person that is like using those, considering maybe variability on the properties. For example, there's this paper that ESI published with Michael about this pillar collapse, where they like plot the 2 pillar strength formulas, one considering like the rock without discontinuities, and one assuming the worst case scenario, but maybe like trying to do that, but also trying to account for the potential variability for maybe the joint orientation. So it is not just a best case scenario and a worst case scenario, but you can actually start to consider maybe like what's the name of this, intervals of confidence, I think it would be interesting to take into account that too, and it wouldn't be that difficult.
I think that's a good idea. And you also brought up an important point I neglected to mention, which is that most of what we're doing right now does not consider any kind of complicated fracture or joint network. We are looking at certain things like weak bands or the influence of a single prominent discontinuity or bedding. But the complication added with just, we'll say, random joint networks added to this is, I think, beyond the scope right now. But in low stress environments, most of your failure is going to be discontinuity driven. So it's going to come out in the end that you're going to have to consider these separately. So what you're doing, for example, I think in 3-deck now is going to be very valuable in that regard. But yeah, for us, we're looking for more broad stress-based failure patterns. But yeah, for sure, it does need to be incorporated at some level in your engineering analysis. And I think you're right about that confidence interval being a good way to approach, just in general, what's stable or not.
I don't know if there's anybody from the audience that would like to ask a question. I think we have some people from Canada. We had some people from Colorado School of Mines as well, or maybe some of the undergrads. So I think there's no more questions. So thank you very much, Brent. Thank you, Michael, for being here. Thank you, Dr. Westman, as well. I think it was a very, very nice presentation, and I hope we can like keep in touch and keep like this talking about rock mechanics and how to improve health and safety in underground mines. So thank you very much.
Thank you, Aman. And yeah, thank you everybody for showing up.
Thanks,
If you
Brent.
need to
Appreciate
contact
it.
me, there's my my email on that slide. Just any questions, let me know.
Thanks, Brent.
Thank you, Brent.
Thank you.
Thank you everyone for being here. Thank you.
Thanks, you guys.